Hello everyone, I'm Pablo Manovi,
My name is Henry Cruz.
I'm Brian Smith.
and we are Team Seads. Right now, public utilities are pushing this idea of demand response, but they're expecting consumers to implement it for them through this idea of time of use pricing, critical peak pricing, and market pricing in a tiered system, which really don't make any sense. And as it stands right now, there's no real way to close the loop between billing and consumers in a way which really makes sense for the consumer. You know, if they want this demand response to work and they're relying upon consumers to do it, there needs to be something which effectively gives the consumers the information they need to do that. So what we've done is created the Seed framework, which is a combination of a research tool for data scientists to create those methods for consumers to get the information that they need, and a consumer-oriented device upon which we can integrate those technologies. Right now, just to give a perspective as to where this technology sits, Smart Grid Technologies is a smart meter which gives you 15-minute data with a very large delay. There are things that you can do to get more information out of it, but it requires a non-standard interface and really is not intuitive.
In designing our devices, we wanted to create a basis for projects with similar core components. In doing so, we were able to create a research-based device as well as a consumer product. The research-oriented device is able to get the signal and then it spits it out over USB to our computer. This is so that the researcher is able to do whatever they want with the data. On the consumer-based product, what we have is we take this signal and then we do computations on it to get the RMS power readings, and then we send it off to the server.
So what we have is a system which creates data that's not only rich, but also big. I'm going to define that as we go forward. To get this rich data, rich in the sense of spectrally dense, we needed a digital acquisition unit. This digital acquisition unit is a setup of two modular boards with an analog front end, which is shared across all hardware components in our framework, and includes an acquisition system which facilitates acquisition, buffering, and transmission over USB to any host platform, be that a PC, a Linux-based computer, or an embedded system. The analog to digital converter which we use allows simultaneous sampling of multiple signal channels and gives us 24 bits of accuracy at 125 kilosamples a second. In practice, we get 109 decibels of spurious-free dynamic range, meaning that not only do we provide a very dense set of data for data scientists to work with, but also something that's very accurate. As we were essentially building a test tool, we needed to not only develop it, but verify that this tool gave the kind of properties which we'd expect it to. So what we did was create an active load which amplified a bandwidth limited square wave excitation current, and we swept it from 0 to 16 kilohertz. In this particular example, we had it set up for a 16 kilohertz bandwidth and sampled it from 0 to 16 kilohertz. And we took a short time Fourier series representation of it. And as we'd expect, we'd see the fundamental tone and all of its harmonics sweeping up with it, which is what we'd expect. This not only verified the acquisition unit, but also the current transformers and essentially the sensors which we were using. Now, why is that important? Why is it important that we have dense data? When we're looking at current and voltage on a system, we need to not only get this, we need to not only have a comparison between the absolute sort of current that you're using, but get an understanding of what's happening when you turn on devices. As you can see here, there's voltage and current. The voltage is small here because we're drawing thousands of watts and they're at the same scale. But if we don't have a dense system, we can't do this, where we step into it and start looking at what's exactly happening on this current waveform. This is very much different from this linear ideal of a sinusoidal current. If we take this and step back into Fourier analysis, we can see that when we turn on and off devices, we get a lot of information. There's a whole bunch of fundamental tones and EMI bursts, which data scientists use in disaggregation techniques that look at signature-based analysis and machine learning techniques like k-nearest neighbors or k-means. On the Seed Lite, our consumer-based device, we have a basic disaggregation technique integrated into it, which simply looks at different circuits. And what we hope to do with this device is give the other side of the data, which is big. So we want dense data available to people, but also big data available to people. Big in the sense of having it being taken from a whole bunch of different sources around the world. One big difference between the Seed Heavy, which we call it, or the Seed Light, is this Wi-Fi stack.
So on the consumer device, we want to be able to send data through a wireless medium for ease of use. The Wi-Fi chip sits between the application processor and the cloud. We chose this chip because it was low cost, as well as the supporting development community. It is a standalone chip, and it has been used as a data communication solution for many projects. What it does is it translates UART data into an HTTP post to the RESTful framework.
These packets are then intercepted by the web server. The server was designed to have a generic interface and a scalable framework. This was achieved by running the servers on the Amazon Compute Cloud on a Django implementation. Interfacing with the database is the Django REST framework, which is a library that exposes our API in an interactive way. As you can see, this interaction is intended to allow developers easy access to the framework if they wanted to integrate a new type of device into the system. In this example, we're getting the properties associated with one of our connected devices. In our implementation, we created an application that is intended to do meaningful things with the data. What we're trying to do with the system is educate the population. We want to provide the public with tools that enable them to better understand their home's energy use. We can do that by separating the energy use by circuit, allowing a user to isolate, for example, their bedroom. Our aim is to suggest ways through which a user can save energy. For example, we can provide the user with a cost comparison of their bedroom versus other bedrooms in our database, suggesting they may be able to save some money if they purchased more efficient appliances or by altering the way they use their bedroom.
Right now, we've integrated this disaggregation technique as an example for data scientists if they want to use this framework. We're hoping that this framework will allow people to integrate new technologies into it and to sort of take our example and just drop in what we hope for them to produce. We have a few people that we're working with right now that are very interested in using this, and they seem to enjoy the kind of RESTful API which we provided them. However, it's important to note that since we've created this as a generic platform, it's also a possibility to include different kinds of data, say water usage or any kind of event. At this point, we'd like to open it up to any questions that you may have, and we invite you to join us outside where we can show you an in-depth demonstration of our UI, if you like.